profesorze.
Okay, one technical remark. You don't have to take notes because all the important formulas are available on my homepage, and I will cite the sources of these formulas. So you better listen and don't write this up. Why electricity and magnetism? Because this is the most important part of physics for humans. Maybe for other civilizations it is different, but humans see the world and not only see but feel, not only feel but smell. This is all electromagnetism.
And also understand.
And also understand, of course.
Those who can understand.
That's right. All the important connections back and forth are in terms of electromagnetism. Okay, so I have this nice quotation here that is a good preamble for this lecture. And I cannot refuse myself. And I will show this portrait of James Clerk, Maxwell, and there is a very nice biography, and there is a quotation from this biography, one who has enriched the inheritance left by Newton and has consolidated the work of Faraday, has clearly earned his place in human memory. 2 years ago we celebrated 150 years of Maxwell Equations, and I gave this lecture then. Now I will not continue much, but I wanted to show you just one sentence, maybe two sentences, from this extremely important paper by Maxwell. And it says, after he wrote the Maxwell equations, he realized that there is a miracle. And this miracle is described here. The velocity of light deduced from experiment agrees sufficiently well with the value of V, deduced from the only set of experiments we as yet possess. The value of V was determined by measuring the electromotive force, nothing to do with waves, with which condenser of known capacity was charged, and then discharging the condenser through a galvanometer so as to measure the quantity of electricity in it in electromagnetic measure. The only use made of light in the experiment was to see the instruments. So Maxwell also had sense of humor here. And this set of lectures will be about these equations, the Maxwell equations, the way they were written by Maxwell. Of course, he did not use the Gibbs notation, but the essence was the same. He wrote it in components. The important part is that you see that there is no 4 pi, there is no speed of light in these equations that people later introduced mistakenly, in my opinion, which are not necessary. The contribution of Maxwell is here marked in red. The equations were known before, but there was this missing term, and when Maxwell wrote them, he realized that it would be much more symmetric to have another term here, and he added this term, and the rest followed. Now, when we see these equations on the screen, let me now talk about these equations from a very fundamental point of view. I will start with dimensions, units, and conventions. So we have these equations. The question is, what are the dimensions of these vectors that appear there? In order to see this, I will write these equations including the sources because this helps a lot. So we have the equation, then we put here the source, and there is another term here which includes this source. The divergence of E is rho. Now, students are often confused because there are so many dimensions here, units, but this is all very simple if you start from the right point. So let me start with J here. J is the current density. Now, we all know that currents are measured in amperes. So we start with the unit of current, A, the ampere. Now, this is not exactly the current, but the current density, because it depends in general on R and T. So we have the current density. If this is the measure of the total current, then the current density, and of course the current is flowing through some surface here, the dimension of this will be A divided by meter squared. And if we start from here, we can then proceed and recover the dimensions of other objects in these equations, because we were taught in the school that dimensions must match. And many
In
things
old school.
can be discovered.
In modern school, there are no units.
So this is A over meter squared. Since the derivative is 1 over meter, that means that this is J, that H is A over M over meter. Ampere over meter is the dimension, the unit of the magnetic field. Now, we know that, then we can proceed and we can say something about the dimension of D. However, we also have this equation, which is quite nice, because it tells us that since the charge is measured in coulombs, and this is the charge density, therefore rho has the dimension of coulomb over meter cubed. Again, the derivative has 1 over meter, therefore D has the dimension of coulomb divided by meter squared. And already here we see that we have two kinds of vectors. Namely, vectors that are per unit length and vectors which are per unit surface. Therefore, this is not exactly a vector, regular vector, because it's per meter squared, so D is the flow. The flow density, something is flowing through the surface, and that is why this is meter squared. And what is flowing? Charge. Charge is flowing through the surface, and that is why this object is called the displacement vector. The displacement means moving the charge through a surface. Now we can go further and look at the other equation, which sometimes is called the Faraday equation, namely dB equals minus the curl of E. Now here again we can start from E. This is the electric field, and the electric field is something that moves current. Therefore, the unit is, I hope, well known, namely the unit of E is volt per meter. So again, we have this type of a vector, like the H vector, which has unit of length in the denominator. Therefore, this is this kind of vector. Now let's go further and see what is the dimension of B then. B, of course, we cannot guess much by writing this equation here, saying that the field B has no sources, because there is 0 on the other side. However, if this is measured in V over M, and we have another M in the denominator, so we see that we could say something about the dimension of B. However, this analogy here with the Gauss law here helps to guess perhaps the right form of the dimension of B. B again should be this type of vector because, as I mentioned, m squared appears in the denominator, and the unit of B then is the unit called Weber divided by meter squared. That's the unit of. So that much about units. This was just a refreshment because everybody, I think, knows it. However, I would like to stress one more point here, which is worthwhile to be kept in mind. Namely, there are several conventions here, which are not really fundamental laws, but they are human conventions. On other planets, if civilizations exist, they may have different conventions. What are the conventions? The first convention is here. Namely, somebody long time ago decided that electrons have negative charge, which is a convention. We could call it positive charge. Nothing would be different. Electrons should
have
be.
to tell that the protons have the negative charge.
Then protons would have negative charge. But since electrons were decided to have, for some historical reasons,
and Mr. Słodowy will have a problem.
Tak, yes.
Because
So, physicists decided that electrons have negative charge. Therefore, already in this Gauss law, that fixes the direction of D, which is not fixed by nature. So we have some charges inside here, and then we have a flow of the D field through the surface. However, we don't know which way it's flowing until we decide what is positive and negative as far as charges go. So this is the first convention. Decision that charges of electrons are negative. What is the second convention? Well, right-handedness of humans. Namely, this is the convention of most humans. This is the convention. What is the meaning of the curl? To define the curl, we use the right-handed law. And this fixes, so this sign here, again, is not in physics, really. This is human convention, that it should be minus, because we decided that the curl, in other words, where is this seen? This is also seen perhaps even better here. This part here is the Ampere's law. And Ampere decided that the magnetic field is going in the right direction around the wire that has current in it. So that much about Maxwell equations, as Maxwell wrote them, from the point of view of dimensions and units. And again, I would like to stress that the original convention of Maxwell is the simplest one. You don't need to remember where is 4 pi, etc., etc. Now, 4 pi, of course, some people thought was convenient because the sphere has the total angle 4 pi, and this is more or less the origin of this 4 pi here. So, we fixed the problems of units, we fixed the problem of conventions, and now we can proceed with Maxwell equations. Maxwell equations, as written here, are not complete. One cannot start solving these equations because there is one important missing ingredient, as you all know. Namely, we must say what is the connection between the vectors and the densities. And this is a very tricky subject which is misinterpreted very often. Namely, you all know that in a textbook you can find the formula. I talked about this some time ago, but I think that the audience is to some extent new, so I will repeat this argument again. This is a good vector, volt over meter. This is the density, Coulomb per meter squared. Not only the dimensions should match, but also the geometric meaning of these objects must match. You cannot compare the flow through a surface with an arrow. These are different objects. If you treat this equation naively, you run into problems, you make mistakes. The simplest way to make mistakes is to consider, as is often very convenient, this equation in spherical coordinate system. In spherical coordinate system, we have, instead of x, y, z, we have r, theta, and phi. And the question then is, can we retain this formula in the spherical coordinate system? The answer is no. And I will comment on that in great detail. Because of different geometric properties of these objects. There are various tricks, not, of course, physicists are smart. They don't make stupid mistakes. So, to avoid these mistakes is to introduce two kinds of coordinates of a vector. Namely, one calls them physical coordinates or something like that, and then one, being careful, will not make mistakes. However, if you know really the origin of this problem, one can resolve this quite easily. Not only the problem of spherical coordinates becomes clear, but also the problem of any coordinate system becomes clear. And to go back to Maxwell equations, I would like to say something which is perhaps not appreciated quite often, that these equations have the same form in any coordinate system you can think of, including curved space-time, including general relativity. Nothing changes in these equations, except that the derivatives here are with respect to these coordinates that you happen to use. The meaning of this depends on the coordinate system. Usually one associates the derivatives with the Cartesian coordinates. However, this could also be the gradient in spherical coordinates, and the equations do not require any changes, any modification. They are still the same equations. Now, again, going back to this formula, how do we resolve this problem? And then I have to use something that perhaps you wouldn't expect to hear on this occasion, but that's the best way to remember and to see what's really going on. Maxwell equations can be derived by a variational principle from a Lagrangian. That's the way physicists like most, to have a Lagrangian, and then we can proceed and write the equation. So what is the Lagrangian? Well, the Lagrangian is minus 1 over 4 f mu nu f mu nu. This is how it's written usually, and f mu nu here is defined in terms of derivative of the 4-vector potential. So we have this definition of f mu nu, and we write this, but that is not something that will help us a lot when it comes to general coordinate system. Namely, there's a problem. What is the connection between this object and this object? This object we define, we will not change this. But we have to say something about f mu nu. The indices are here in the upper position, and that means that we have to raise this indices, and there are rules how to do it when you study more generally the geometry here. In the simplest case, it is the Minkowski geometry, but I would like to go a bit further and introduce any geometry I can think of, and then f mu nu becomes the same good f mu nu here, except that I call the indices by different letters, and these indices must be then raised using the appropriate metric tensor. Now, if you don't really want to follow this kind of stuff, you can treat this as a remark which is not necessary to understand what will be the subject of the remaining part of this lecture. However, this is indeed a very simple way to rewrite this Lagrangian in a form that is now compatible with any kind of coordinate system. And this new form is the same 1 over 4. But here we also need something which I call square root of minus g, which is the determinant of this metric that we have here. And now we rewrite this using our formula for f mu nu upstairs. So we have f mu nu downstairs, f lambda rho downstairs, and we use then g nu lambda and g nu rho to make all the indices properly positioned. And this miraculous formula is the simplest way to treat electromagnetism in any coordinate system, including, as I said, curved space-time, like Schwarzschild solution, curved solution, whatever. The Lagrangian is always the same. It has this form. What is to be chosen is the metric. Once again, what is G? G is the determinant of G mu nu. And minus is necessary because this determinant is negative. The simplest way that it is negative is to write it in Minkowski space. Then we have 1 minus 1 minus 1 minus 1. 3 minuses is minus, so we need the minus 2. Now, let's go back to Maxwell equations. The variational principle requires the basic quantity that is being varied in order to find the minimum or stationary point of the Lagrangian, like in classical mechanics. So we have the Lagrangian, and we vary this with respect to the potential. You can do this exercise yourself write down this, and I will just complete this by writing the final answer. The variation must be equal to 0. So the variation will annihilate f mu nu because it's linear in A. And there is an additional derivative here, which will be by partial integration turned over to the rest here. And what happens is the following thing when we vary the Lagrangian. Here is the Lagrangian, and this is the variation of the Lagrangian. Minus disappears, 1/4 disappears, but we still have square root of minus g. We will have the derivative here because, as I said, we vary with respect to A, so the derivative must be turned over to the other side. And what is left here is this object, which, before I use this formula, now for a general metric I have to use a different name, because this will in general be a completely different object. It will have all the coefficients of the metric tensor. So let me call this H mu. And this must be equal to 0. And these are Maxwell equations in general relativity, in spherical coordinates. You don't have to think, you have to calculate. All the ingredients are here on this board. H mu nu is defined. If we are just doing spherical coordinates, then the metric is quite simple. These are coordinates on a sphere. So we have the coordinates r, theta, and phi. And the coefficients here depend on r squared, on sine theta squared, all that stuff that you get if you express the length. Now I'm talking about the simplest case, no general relativity, just different coordinate system. And the r squared in spherical coordinates is the length of r squared plus r squared d theta squared plus r squared sine squared theta d phi squared. Now these are there's one here, so one component of g is 1, the other component is r squared, the third component is r squared sine squared theta, and from these components you build the determinant, and from these components you build this object, and then everything checks, and we have here epsilon, which is not a number, but is a function of all these components. It's a complicated function if you go to more complicated metrics, but it's all contained in this simple formula. I will come back in January to these problems, and we will discuss something more complicated, but for now, I hope that I conveyed my message that the constitutive relations are not a simple matter. These are not just some numbers that you take for this epsilon, but you have to think what is the coordinate system, etc., etc. It is possible to express these constitutive relations for a given choice of the metric, but the equations are quite complicated because here we have these 4x4 matrices and you have to do it. However, it all works, and we know now what are some subtle points that must be kept in mind. But now, for a certain time, I will just deal with Maxwell equations in flat Minkowski space, no complications, and in this case we can somehow figure out that d equals epsilon E can be given some meaning. So what will be the main tool during all these lectures, the unified tool that will help not only to treat classical electromagnetism, but also quantum electromagnetism in a unified way? This tool was discovered by a Polish physicist, Ludwig Zilberstein. Maybe even it was known to Riemann. That is why I call this object Riemann-Zilberstein vector. However, Riemann died prematurely, and the idea occurred in lectures that were given by Riemann, but then wrote down by Weber, another Weber, from the one that gave the name to the unit. So let's pay tribute also to Riemann, and we have Riemann Zilberstein. Zilberstein discovered this in 1907. He was not aware at first of the work by Riemann and Weber, but in his second publication he mentions that perhaps Riemann knew about this. What is this object and why it is very convenient? We all know from the first year exercises in physics that it's convenient to use complex variables to describe oscillations, because then certain formulas are easier to obtain. We know that the solutions in terms of complex numbers of linear equations with constant coefficients are a very convenient tool. Therefore, this useful tool is very frequently used in electromagnetism. We write objects like this, e to the I k r minus I omega t. And then what people say, if you open a textbook, the physical interpretation is only valid for the real part, because complex numbers have real and imaginary parts, and imaginary part must be rejected. Now this is a waste of our effort, and Riemann-Zilberstein vector helps to resolve this unnecessary waste of resources. Now everything is called resources. So we have resources and we would like to use them without rejecting anything. And the way to do it is to introduce this vector. This vector is built in the following way. D divided by square root of 2 epsilon plus imaginary unit I b to mu. This is the definition.
In Cartesian.
Y epsilon.
In Cartesian form.
I will comment on that.
You just mentioned this.
No. Not quite. This will be explained in more detail. Not in Cartesian coordinates. No. But y epsilon and mu? Well, because b and d have different dimensions. So we cannot just add them. We must fix the dimensions. One is in Coulomb per meter squared. So meter squared is okay because this is Weber. But the difference between Coulomb and Weber is in these coefficients. Y square root of 2. Without square root of 2, it would be equally well. However, There is one reason, very simple, why square root of 2 is convenient, because this is nothing else but the energy density as a function of R. The energy density is the square of the d vector divided by 2 epsilon plus the square of the b vector divided by 2 mu. That's the energy density, the Hamiltonian if you wish, and that's the reason for the square root of 2.
You take for now that epsilon and mu are scalar.
Let me proceed now before I get into something more complicated in the simplest case of free space, and then I only have numbers that are taken from the tables, not pure numbers, they have dimensions, of course, but how is this related to general coordinates will come later. So we have this vector f defined as Ludwig Silberstein wanted it, and nothing will be rejected. The real part is electricity, and the imaginary part is magnetism. So we do not waste any resources. We have both these parts included. And what is now the set of Maxwell equations expressed in terms of f? All we have to do is to take the equation for the time derivative of b and the time derivative of d on the left-hand side, dt. Here we will have the vector f with some appropriate coefficients, and on the right-hand side, when you do it, then you can also use in the vacuum the important relation 1 over epsilon 0 mu 0 square root is equal to c. That's correct. So we have c here. Now we have a curl of f. I. This will be in free space. To keep the possibility that we still have some medium or curved coordinates, I will modify this slightly, and I will say, well, there is a vector g here. And what is the vector g? The vector g is made of the electric field and the magnetic field, with appropriate coefficients to match the dimensions. Now, this equation, if we also know the connection between f and g, which are the constitutive relations, we have achieved what we wanted, that is the complex structure of our equations, and both parts, real part and the imaginary part, have a physical meaning. So now this equation have solutions of this sort that I have written before, e to the I kr minus I omega t. This is a solution of this equation. Its real part is the electric field, and its imaginary part is the magnetic field. So we gained something by this complexification, and it turns out that it is extremely convenient for future considerations, including the quantization of the electromagnetic field. Now we are at the level of classical electromagnetism. Nothing has changed. These are the Maxwell equations complexified for mathematical convenience, if you wish. So, this is the Riemann-Zilberstein vector. As I mentioned, don't take notes because all the details you can find in our review paper on the role of the R as vector, and this paper is available on my homepage at the Center for Theoretical Physics, so you can illegally copy it because
I think that for educational purposes it's legal anyway, so it should be.
yes, I know that. Michael Berry, of course, put all his papers on his homepage and explained that everything is available, and the reason for that is education, to educate people. You don't have to worry about the proper rights. Okay, so in this paper, everything that I say here, when it comes to some details, is written down. Okay, so we have complexified Maxwell equations, and now we can proceed and do some simple exercises just to show you how powerful this method is to find solutions to Maxwell equations. So at first, as I said, I will deal with the free space, in which case I can identify F and G. And these are the equations we will be discussing now for a while. Well, what is this? This is a set of linear differential equations with constant coefficients. So there are simple methods to proceed. You don't have to worry a lot, but just go ahead. What is the best way to start? The best way to start is to say that every solution of this equation can be written as a superposition of plane waves. Plane waves form a complete set of solutions, and every mathematicians would say every regular solution, whatever that means, can be written as a superposition of plane waves. So let me write down this superposition. Different plane waves are labeled by the wave vector. So the integration, the superposition, will be an integration over all possible wave vectors. For reasons which will become clear in a moment, I include the normalization factor, which is familiar when it comes to Fourier transforms. In one-dimensional Fourier transforms, it's square root of 2 pi, and this is three-dimensional Fourier transform, therefore it has square root of 2 pi raised to the power of 3. Now I do something which you may consider peculiar at this level. However, in order not to make changes when I go to the quantum theory, I introduce the factor which already smells of quantum theory because it has H bar in it. Now it's just a factor. Since this is a linear equation, I can multiply by any number, and it is still a solution if I have one. So don't worry about this factor here. And now we have the Fourier transform. Therefore, but I will write this Fourier transform already in the form that is the convenient one. Namely, this is a vector. So we need a vector here, which I call E, and this vector, of course, depends on K. And certain miracles happen here, which have even been misunderstood by some Chinese physicists who quarreled with us that this must be wrong, because here there's only one vector, and we know that there are two polarizations, so there must be two vectors. not true. Now we have amplitudes here, which tell us how many of this particular brane wave is included in this solution. So this will be a function of k, and there are two such amplitudes, so one will be called plus, and the plane wave here is I kr minus I omega t plus. Why there is a second part here? Because I will always assume that omega has its standard form c times the modulus of k. And there is no reason to suppose that the general solution has only one sign of frequency. General solutions should have both signs. And this is included in this formula. In the following form, there is a second term here, which has reversed signs here. Okay. Plus I omega. For future convenience and for the easy connection with the quantum theory, I will call this amplitude complex conjugate. And this is, at this level, this is just something that looks quite arbitrary. So what are these two amplitudes? These are the true degrees of freedom of the electromagnetic field. Electromagnetic field has 6 components. We reduce this, I'm sorry, it has, at first it has 12 components because we have 4 vectors. Then we reduce this to 6 by using the connection between the constitutive relations. Then we have 6 real functions. Now these functions are then restricted in free space by divergence relations. This is 0 and this is 0. So 6 minus 2 is 4. We have 4 real degrees of freedom, and these functions are complex. Therefore, 2 complex functions is the same as 4 real functions, and they describe the true degrees of freedom of any free electromagnetic field satisfying the Maxwell equations. And this way of looking at the solutions of Maxwell equations is quite convenient because, as I will show later, we can discover various properties of the electromagnetic field when we use this representation. Now, going back to this vector. In order to satisfy the equation here, we must impose certain conditions. Now, the derivative with respect to time produces either minus I omega or plus I omega. Here, so we have to use this and this equation. The derivative with respect to space produces the k vector. So we have the following algebraic equation that this vector E of k must satisfy. So here we will have derivative of t will be omega in this case. So we have plus or minus omega on the left-hand side. Then we have the vector E. Okay. And this must be equal to c. Then we have the derivative here, which will produce plus or minus sign, depending on whether we act on this term or on this term. And the curl is just k, of course I here, coming from I, k cross E. You see that these signs are identical. Therefore, I can erase them because the equation is the same. And this is a set of three algebraic equations that this vector must satisfy.
Where from is I? The unit I.
Because I, C, the units are okay because Kc is the same as omega.
But I? Why I?
Why I? Because I differentiated with respect to K.
But on the other
with
hand,
respect to
on
R.
the other side, you also differentiate over T and
But there was an
There
I
was
here.
I here, okay, so.
Sure.
So this is the equation. At first it would seem that this equation has no solutions because this part is perpendicular to K. So if we have a vector which is perpendicular to itself, must be 0. However, it's a complex vector. Therefore, everything is okay. And I will write down a convenient solution later. Now, this is the whole problem of solving the Maxwell equations reduces to solving algebraic equation for the components of this.
In a free space without sources.
In free space without sources. That I stress. That's great. So here we have this, and it will be convenient to have vectors E normalized. Since these are complex vectors, we normalize them in such a way. This will be assumed to be equal to 1. This only fixes the normalization of F. Now there's a lot of interesting mathematics which I will not go into, but I will just mention. Now, this is something that represents the electromagnetic field in space and time. So we know everything about this object from the special relativity point of view at least. We know how the electric field transforms, we know how the magnetic field transforms, they mix under Lorentz transformation, they rotate under rotation. So we know the transformation properties of this object. Now, this is a fixed vector. It does not transform at all. Just given as a solution of this equation. So the whole problem of transformations is connected with these amplitudes. However, these amplitudes are just complex numbers. So we have a very peculiar, first it seems, situation that this whole complicated transformation laws of electricity and magnetism, if you can open a textbook like Jackson or whatever, you find that these formulas contain the mixing, as I said, of electricity and magnetism. It must all be contained in the transformation properties of these Fs. What can they do when you change, say, coordinate system? The only thing they can do is that they get multiplied by a number. And this is the truth. These are objects that have very simple, basically, transformation properties. When you rotate the coordinate system, they pick up a phase factor. When you change the Lorentz frame, they also pick up some factor. And these are the objects that, for example, Eugene Wigner studied in 1939. And of course, these are examples of something much more general, namely, how do amplitudes of that sort transform for any relativistic object, not just for the electromagnetic field. And this is the simplest and very important special case. F's are just amplitudes that have very simple transformation properties. Transformations properties will be later mentioned, will play a role. Especially they are important for the understanding of such notions as helicity, angular momentum, orbital angular momentum, spin. All these concepts are contained in these formulas. However, to recover the proper meaning is not trivial, and many people make mistakes here, confusing, for example, helicity with polarization, etc., etc. One can find scores of papers written even by knowledgeable people who do not quite understand the significance. So let me give you the first glimpse of this. What will come next is the explanation of helicity. What is helicity of the electromagnetic field? Helicity of photons will come later. Now we will not.
If we slowly
Yes,
close.
that's right. This is my set of few sentences which will end up this lecture. Namely, helicity is in these two amplitudes. This is the helicity plus, and this is the helicity minus part of the electromagnetic field. This is the basic fact. Polarization is a secondary property, like linear polarization, etc., circular polarization. This is all a secondary notion. Now we take Wigner, who said that there are two, for photons, there are two representations of the relativistic Poincare group, namely the representation with helicity plus and helicity minus. Helicity is something that has a picture of a screw, and this indeed will be shown to be the case. This is, of course, as I already mentioned, there's no mixing between these two. They transform separately, helicity plus and helicity minus. And what is this vector here? When you compare it with other polarization vectors in textbooks, you find that this actually is a vector of circular polarization. Only one circular polarization. So how come, and this was the confusion that these Chinese physicists made, where is the other polarization left hand? It's a convention, because I have chosen I here, not minus I. If this plus was replaced by minus, everything would go as before, except that the interchange of two helicities will occur. There is no reason to double this and to consider both helicity, because every set of electromagnetic field vectors can be represented by a complex function. And it is my choice to choose the plus side here. And the rest is mathematics. Thank you. The rest in January.
Thank you very much.